Hello, welcome back to three-phase circuit analysis. We're going to solve the exact same problem that we did in the last section, but the only change that we're going to make to it is it's going to be a negative phase sequence. So everything that we're going to find in the last problem, we're going to solve it again. But it's not going to be quite as painful because we've solved all of this stuff. So in some cases, I'll just be able to erase something here or there. In some cases, I'll have to erase a little more. The reason I'm actually doing that is because a lot of students think that if it's a negative phase sequence, they'll just change the sign here and there. Oh, no big deal. I made a mistake. Who cares? I'll just change the sign or whatever. Well, it isn't quite so simple, and you're going to see that. So some values do allow you to do that, but some calculational values are completely different from the positive phase sequence case. So that's why I wanted to leave everything on the board and show you what changes rather than just do it all again from the beginning. So essentially, the problem itself is exactly the same, except what you would see in a problem, instead of ABC sequence, you would see ACB sequence, which means negative phase sequence. The generator impedance, generator voltage, three-phase load impedance, line impedance, A-phase impedance, or the A-phase as a reference is all the same. Everything that we're asked to find is exactly the same. We're finding the line currents, we're finding the single-phase equivalent circuit, obviously. Find the phase and line voltages at the load, the phase and line voltages at the source. And then this diagram, the little cheat sheet diagram that I have here that I always tell you to draw, I'm going to leave it in place because nothing changes. The phase sequence doesn't change the physical layout of how this is drawn. It's just changing the phase relationship basically between the B and the C phases and how they relate to the A phase. All right, so then part A. Let's say we're going to do this problem exactly as we had, pretending that we didn't know anything about the last time. Let's just do it all over again. Draw a single phase equivalent circuit. Okay, so let's go over here and see if what we have applies. So the load impedance is exactly the same as before. That stays the same. The line impedance is exactly the same. That stays the same as before. The source impedance is exactly the same. That stays the same. And the source voltage stays exactly the same too. So it looks like the single phase equivalent circuit actually stays the same. And it does. There's nothing that changes. Even the diagrams here, VAN on the load side, VAN on the source side, all of that stuff stays the same. So when you're drawing single phase equivalent for a positive or a negative sequence, it doesn't apply at all. The A phase is the reference phase, and the phase sequence governs how the B and C phases relate to the A phase. So obviously the B and C phases are affected, but the A phase doesn't change at all. So this part we have to make no changes to. It's exactly correct as is. Now part B, let's go and find the three line currents, AA, BB, and CC. How would we find the line current here if this is a negative phase sequence? Well, the A current is exactly as we have drawn it here. It's exactly the same. So there's no change from the previous problem to this problem when we have a positive or a negative phase sequence to find the current AA. It's the voltage here divided by the sum of all these impedances, which is what we did before. And so it's exactly the same, 40 plus J 30, and so the value that you get for the A value of that current for the A phase is exactly the same as it is before. However, to get the B and the C phases, it's different now because this is exactly why I always tell you to sketch this. One of these days you're going to forget and you're not going to sketch this and you're going to get something wrong and that you're going to not be happy. So the way you do it is, it's not ABC sequence, it's an ACB sequence. That's what changes. Really, that's the only thing that changes in this problem. It means that once you have an A value for whatever it is you're calculating, current or voltage, you subtract 120 not to get a B value like we did before, but that gets you a C value when you subtract 120 degrees. And then going the other way, in order to get to the B values, you add 120. So it's literally the